Numbers like this one can be wild, but modular arithmetic is what makes them simple. Today, we're exploring the magic of modular arithmetic and how powerful of a tool it is. So we say number n is a mod b if n relieves the same remainder as a when divided by b. For example, 37 is equivalent to, not equal to, equivalent to 1 mod 3 because 37 leaves a remainder of 1 when divided by 3, and so does 1. Similarly, we also have 37 is 4 mod 3, right? Because they both leave a remainder of 1 when divided by 3. And it's also equal to negative 2 mod 3. Negatives, yes. Mods can also be negative. And all that means is that negative 2, the remainder when negative 2 is divided by 3, is the same thing as negative 2 plus 3 equals 1 when divided by 3, right? Because if you add 3 to it, it becomes 1. So you can think of it as 2 less than a multiple of 3, which is the same as 1 more than a multiple of 3. Okay, so there are many useful properties in modular arithmetic and useful rules. The first useful rule that we have is that if a equal to something mod n and b equals y mod n, then ab is equivalent to xy mod n. For example, let's say you have something like 9998 times 8887 and you're trying to find the last digit. Now, one way is to multiply these numbers out, and that does not look like it would be easy at all. So instead, because we're just looking for the last digit, all we have to do is find 8 mod 10 and 7 and find that the second number is 7 mod 10. So the product is equal to 56 mod 10, which is the same thing as 6 mod 10. So this works for more than just 10. Whenever we have, let's say, a equals something mod n and b equals something mod n, the product of a and b is the same as the product of x and y mod n. Let's view an example that uses this property. If n is an even integer, positive integer, the double factorial notation represents the product of all the even integers from 2 to n. For example, 8 double factorial 2, 4, 6, 8. What's the unit digit of this giant enormous sum? Okay, so 2 double factorial is just 2, because there's only one integer from 2 to 2. 4 double factorial is 2 times 4, right? All the even integers from 2 to 4. 6 double factorial is 2 times 4 times 6. You understand what it means now. 8 double factorial, like they say, 2 times 4 times 6 times 8, and so on. And 10 double factorial is 2 times 4 times 6 times 8 times 10. And now the power of this, you can just do copy, paste. So we have got now that, whoops, okay, that did not work very well. We have that 12 double factorial is 2 times 4 all the way till 12, right? And so on and so forth. So the question is, find 2 double factorial plus 4 double factorial all the way till 22 double factorial, the unit digit of that. So like we just explored, because we only care about the unit digit and we're multiplying a bunch of numbers together, essentially we are just looking, the product of these numbers, we can just take the unit digit of all these numbers and multiply them together. So 2 is just 2 mod 10, right? 2 mod 10, remember that means leaves a remainder of 2 when divided by 10. That's 8 mod 10. That is 48 mod 10, which is the same thing as 8 mod 10, which is equivalent to 8 mod 10, right? Remember, it's not equal, it's equivalent or congruent. This over here is 2 times 4 is 8, 8 times 6 is 48, and 48 times 8 is equal to 8 times 50 minus 8 times 2. That's 400 minus 16, that's 384 mod 10, which is 4 mod 10. Or actually, actually, rather, why are we even doing this? Remember the property product rule? We can just look at the last two digits, right? Because the product of two numbers, mod 10, is just their individual values, mod 10, multiplied. So this is just the same as 8 times 8 mod 10, which is 4. 4 mod 10, right? Because 64. And this over here, oh, we're multiplying by 10, so it's 0 mod 10. It's a multiple of 10. Next one, oh, multiplying by 10 again 0. All the way till 2022 double factorial. That's 2 times 4 times 6 times 8 times 10, dot, dot, dot. It's also a multiple of 10, which is 0 mod 10. So it seems like after 8 double factorial, all of the rest of them have a 10 in them, so are going to be 0 mod 10. So therefore, all of these are 0, so we don't even have to consider them. So now all we do is add them up. 2 for this first one, plus 8, right? Plus another 8, plus a 4. And that's all that there is. 2 plus 8 plus 8 plus 4. That's going to be 22, which is equivalent to 2 mod 10. So what is going to be our answer for this problem? Yes, the answer is just going to be equal to 2, because that's the remainder. So now let's quickly review this problem here. So the first key idea was noticing that double factorial, just to write out a few terms, look for a pattern. We found the first two values pretty easily. We even used the product mod rule here to simplify our calculation a little bit. And also from there, we just noticed that everything past 10 double factorial, everything past everything past 10 double factorial was equal to 0 mod 10, right? So therefore, the answer is just the sum of all of these ones mod 10, that is 2. And you can check out these written examples in the free Mastering AMC 8 book. The link to that book is in the description of this video. It's a good guide to complement these videos. Okay, now we're going to explore the exponent rule. If a is x mod n, then a to the m is x to the m mod n. Now that might seem a little strange, but let's say we have 37. We're trying to find the remainder when 37 to the power of 38 is the mod 3. Now to do this, all you have to do is, rather than evaluating that, which would take probably a few years, you just have to find 37 mod 3, which is equivalent to 1 mod 3, right? Leaves a remainder of 1 when divided by 3. So this is just going to be 1 to the 38, which is this 1 mod 3. So the key idea is you can replace any number here with its corresponding value in mods. And that you can prove it directly from the product rule. Okay, now let's take a look at this example. Find the remainder when 9 to the 8 is divided by 100. Okay. So there's actually a way to doing this, a more advanced way using binomial theorem. I covered it in my Mastering AMC 10-12 series, which you can check out after you finish this series. But for now, let's use the exponent rule. So the exponent rule states that we essentially, to find 9 to the 8, we'll see how it's used later. But for now, 9 to the 8, that's a giant number, and it would not be a good idea to try and evaluate this. I can tell you. I've tried and it doesn't work. Or it will work, but it will take you quite some time. So here's another thing you can do. Notice how this is equivalent to 9 squared to the 4th power, right? So 9 squared to the 4th power, that's just 81 to the 4th power. Okay, now 81 is kind of big, and doing 81 operations with that, multiplying it, would not be easy. So what we're going to do is use this rule. To find 81 to the 4 mod 100, all we need to do is find the value of 81 mod 100. Now you might be thinking, 81 is just 81 mod 100. What can you even do? The key thing is we can make it negative. And that's helpful because This is equivalent to negative 19 to the 4 mod 100, right? By our exponent rule. And look, guess what? 19 is a lot smaller than 81, so that did help, actually. Now notice something. Negative 19 to the 4, we can rewrite it as negative 1 to the 4 times 19 to the 4. And negative 1 to the 4 is just 1, so it's just 19 to the 4 mod 100. And now we can just do something similar again. This is 19 squared, which is just 361 squared mod 100. And now we use the same rule again. 361 squared, 361 is 61 mod 100. So this is 61 squared mod 100. Or rather, we can let it be negative 39. That's actually going to be better, right? Negative 39 squared mod 100. And now we can do a similar operation. Negative 1 squared, 39 squared. Negative 1 squared is just 1, so just 39 squared mod 100. Now, 39 squared, how do we do that? Well, if you've watched my squared video, you know how to do this very quickly. So the trick to doing these kinds of things is you do 39 minus 25, 14, and then 11 squared, 121, so 1521. Right? So that's going to be this, which is nothing but 21 mod 100. And that's how you make a complicated problem much easier. 21 is our answer. So the key idea here was organizing the exponents and then simplifying this inside term using this rule, right? Because we can just simplify the inside part of it, mod 100, and then we get a much simpler expression. We kept doing that until we got just a simple number, 21. Okay. Now, there's also a strategy where you can combine different mods together. And let's explore that in this problem over here. Find the smallest positive integer that leaves a remainder of 5 when divided by 6. Let's over here. 5 mod 6, right? 2 when divided by 5. 2 mod 5. 2 mod 7 and 2 mod 11. Now this seems very strange. How in the world are we supposed to do this? Guess and check? That's a very bad way to solve this problem. Any smart ways we can think of? 5 mod 6. I mean, look at this. All of these numbers are primes. This one is not prime. Anything we can do about it? Well, what we can do is we can split this up into two different statements. So if a number leaves a remainder of 5 when divided by 6, what does it leave a remainder of when divided by 2? 1. So 1 mod 2, right? This statement means this statement must be true. And similarly, if a number leaves a remainder of 5 when divided by 6, what must it leave a remainder of when divided by 3? 2. 2 mod 3. Basically, we split this up, and the reason we do this is because 6 is equal to 2 times 3. So whenever we have some statement mod, some value that's not prime, we can always split it up. And now look, now this looks a lot easier. 2 mod 3, 2 mod 5, 2 mod 11, 2 mod 7. So if a number is 2 more, let's say n equals 2 more than a multiple of 3, 2 more than a multiple of 5, right? 2 mod 5, this condition here. 2 more than a multiple of 7, and 2 more than a multiple of 11, right? What does that mean? Well, that means that n minus 2 is a multiple of 3, 5, 7, 11. We just subtract 2. That makes sense. And if it's a multiple of 3, 5, 7, and 11, it's also a multiple of their LCM. Remember that from the GCD LCM video. But look, they're all primes, so the LCM of a bunch of different primes is just their product. 3 times 5 times 7 times 11, that's 105 times 11, 1050, 105, 1155. So n minus 2 is a multiple of 1155. So n is 2 more than a multiple of 1155. Okay. But we already have used all of these conditions. But notice how we also have this condition that it's 1 mod 2. So n is 2 more than 1155. Let's list out the possibilities so far. Okay, so the first possibility, and let's write this in modular arithmetic notation. 2 mod 1155, right? So what are the possibilities? N is a positive integer. So n can be 2, n can be 1157, and so on. So notice here that n has to be 1 mod 2 or odd. So the smallest odd one is just 1157. So 1157 is going to be our answer to this problem. So the key idea was first noticing how 5 mod 6 is unlike the other mods, so we split it up into 2 different mod statements. Then after that, we had this logic here, and we found that n minus 2 is a multiple of this, so it's n minus 2 is a multiple of that, of 1155. So that means n is 2 more than a multiple of 1155, or 2 mod 1155. And then we also had this 1 mod 2 condition, so we just tested the first few possibilities and saw that this is the smallest one. And that is our answer. Okay, all right. Okay, next. Find the remainder when 15 to the 1, 15 to the 2, 15 to the 3, plus so on, 15 to the power of 2022, plus 34 to the 1, 34 squared, all the way till 34 to the 2021 is divided by 7. Wow. And now, even if you somehow manage to brute force your way to the other problems, I guarantee you won't be able to evaluate this. I'm sorry, it's just not possible. So then what should we do then? If we can't evaluate this, the extract value, well, actually, technically you could using the geometric sequence formula, but even that would be really difficult because you would have 15 to the 2023. So let's do something smart. And the key thing is no one's asking to evaluate this, just the remainder when divided by 7. And notice, to find the remainder when it's divided by 7, we can just define the remainder of each piece, right? And add those remainders up, the modular sum rule. So what's the remainder when that's divided by 7? 15 to the 1, we can use the exponent rule. It might seem silly to use it here, but for the other powers, it will matter more. Remember, this is just going to be the same as 1 to the 1 mod 7, because 15 and 1 are congruent mod 7, and this is just 1. So 1. Now 15 squared, this is going to be 1 squared mod 7, because 15 and 1 are congruent mod 7. So this is also just 1. And it turns out that for each of these values, this whole giant sequence is the same thing as 1 to the 1, 1 to the 2, 1 to the 3, 1 to the 2022. So every term in this sequence is 1. So it's just 1 times 2022 mod 7 for the first part. Now what about the second part? We do something very similar. 34 is negative 1 mod 7. It's 1 less than a multiple of 7, 35. So this is equivalent to negative 1 to the 1 plus negative 1 squared plus ... negative 1 to the 2021. And notice that negative 1, it alternates, right? Negative 1, 1, negative 1, 1, it alternates. Negative 1 is, then negative 1 squared is 1, then negative 1 cubed is negative 1. So this will just alternate. Negative 1, 1, negative 1, 1, all the way until the last term will be negative 1 because it's odd. And if you remember telescoping, most of these will cancel out. The only term that will remain is the last negative 1, because there's 2021 terms, 2020 of them from 1 to 2020 will cancel out, and we're just left with this last term, and because it's odd, it's negative 1. So this will just be negative 1. And this is 2021. Cool. And what's the remainder when 2021 is divided by 7? Well, there's different ways of going about that. One way is just to divide, but another way you can do is notice that this is 2100 minus 79, and this is equivalent to 0, right? 2100 is a multiple of 7, and minus 79. Now, notice how 79 leaves a remainder of 2 when divided by 7, so equivalent to 2 mod 7. And this is equal to negative 2 mod 7, and remainders cannot be negative, unlike mods, so our answer will then be 5. So 5 is the answer for this problem. A great application of where it comes down to looking at each term separately, finding the value of each term individually, mod 7, and then adding all these things up. Okay, and you can check out all these practice problems in the AMC 8 book, link in the description. We're ready to move on to algebraic number theory. It's number theory problems, except you also get to use algebra because you're using equations and variables. But the key thing is we're dealing with integers. We'll explore that in the next video. You can check it out by clicking the link right there.